Hey everybody, this is Larry. This is April 21st here in New York. Yeah, I wanted, I don't know, I don't usually do this, but I did want to do an extra problem just because I haven't done one in the last couple of days and I just feel a little bit itchy, like some days you just feel like you want to do a little bit more. And that's what I'm going to do today. And today we have 1724, check existence of edge length limited paths 2. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. I haven't done this one yet. It's a random one. It is a hard problem, so hopefully it doesn't take too long, but it should be okay. I hope, because I am always optimistic. Well, not always, but enough. Alright, let's see. An undirected graph of n nodes is defined by edge lists, where edge list of I is equal to this thing. Okay, we have an edge list. There may be multiple edges, and they may not be connected. Okay. Do we get all the edges? We do get all the edges in the beginning. So we have a query. Return true if there exists a path from P to Q such that the distance is strictly less than limited, and so forth. Okay. So for example, we have this where we added all these edges. Okay, fine. And then we have a query on. Man, this is hard to read. Oh, these are the queries, I believe. And it's 2 to 3 with 2. Limit as in less than limit. Okay. Such that each edge on the path has a distance strictly less than limit. I mean, I'm trying to think why the default shortest path doesn't work. I'm just trying to make sure that I read this correctly. Have a history of misreading things, so definitely want to avoid misreading even more. But let's see, right? So 3-2 is going to be true because there's an edge 3 which has a distance of 1, and it's the edge of the. So yeah, I think shorter. So the reason why shortest path would work is because it is a greedy thing, right? The distance between any 2 points is just going to be the shortest thing between them, right? And well, I say shortest path, but that's not even necessary. Or I mean, I say shortest path in a weird way because shortest path in my head is just the shortest based on the cost metric. And the nuance here is that the cost metric is just the rate of the longest path, right? And what does that mean? I mean, the idea that I'm having right now is that it is a minimum spanning tree thing because as you merge components, then you can construct what the limits are. And in fact, I think if there's a non-query version of this, this would be a very straightforward minimum spanning tree problem, right? Where you would just do the query in order. But because you have to do live queries, it may be a little bit trickier that way. There are only 10 to 4 number of edges, but 10 to the 4th number of nodes. So the tricky thing is that you can't really do, like you can't store to n square number of things. So you have to do something a little bit smarter. Minimum spanning tree still makes sense. No, does it? No. No, minimum spanning tree makes sense the same way that the shortest path idea makes sense is because of greedy, right? The reason why minimum spanning tree works is because of the greedy algorithm, and you will connect everything with the components that you can. And then the question is, how do you do these queries in an efficient, fast way, right? What is this sub I? I guess it doesn't really. Oh, it's distance. Okay. I guess it doesn't really matter. I mean, I don't think it matters that much because you just sort the edge list, right? Okay, so let's say we do a sort the edges. We do trying to think. Right. Okay. So let's say you have 10 to the fourth edges, and you do a sorting on them. That's basically free. It's E log E or whatever. The question is, can I store enough things to answer the query in a faster way? And I want to say that maybe, and I don't know how I don't know, because the thing is that whenever I think of a heavy machinery answer, I'm always, at least for on the Leetcode level, want to rebel against it a little bit, but it does come up randomly. And the idea that I have is binary lifting, right? Like, okay, you construct the minimum spanning tree, and then now you do a binary lifting to get. Oh, huh. I guess that is true then, right? Because I forgot about, so for binary lifting, I forgot that basically one of the construction is going to be RMQ, right? Remote, or not remote, range minimum query, and range minimum query is has a reduction to LCA, which is lowest common ancestor. And you could definitely construct a graph. Maybe. I mean, it's kind of, I don't know. But these are like very heavy machinery, so I feel like I want to make sure that I need it before I need it. You know? But okay, so my idea is going to be create a minimum spanning tree. Find the LCA. The LCA will determine the shortest path, and you find the LCA with binary lifting. Do we need to? I mean, we can also convert the LCA into RMQ. Is it worth the effort? And then basically you can enter this as a RMQ. But I think this, wow, this is, I mean, it's doable, and I think all the pieces make sense. It's just that it is a lot of programming that I don't know. It kind of maybe regret opening it for a second. I did want it to challenge it a little bit, but I mean, all the ideas is right. It is just very annoying. Okay, fine. All right. All right, let's do it. And here, just to be clear, I am trying to do everything off memory. Maybe I will get stuck in the future and then, consult some stuff. But for now, like I said, I think I said on the other video, actually just earlier today, I do not have, I mean, I do have code written just from the past, but I don't have any templates on any of these. So we'll see how far I get before I need to. Minimum span tree part is fine though, so I don't worry about that part. But sorry, let me Let me set aside some stuff because uh, I was hoping to get a easier problem, to be honest, and we're already 10 minutes in and I haven't even started coding yet. But I think the idea is right. It's just I'm trying. Is still an easier idea? Probably not. I feel like um, how do I do the LCA? I mean, I know I do LCA. I'm trying to think if I remember all the components. LCA. How do I do the LCA between two nodes? You go up. I mean, at least in a non-linear kind of way. So you do the, you double. Oh, I remember. Okay, right. But that's tricky. Okay, it's been a while though. All right, let's do it. What is this? Edge. So we want to sort edge list by the distance. So use that should be fine. The UV I don't care about it. Right? Now for UV in weight in edge list. So now we have to do a minimum spanning tree, right? So now we have a union find, right? So how do I get the actual tree? I forget. Oh, right. Okay, yeah, I know how. Yeah. Right now I'm just typing out union tree, find stuff, right? Maybe, like I said, maybe I should have templates for this. I mean, I do, but the point of this is to learn. So hopefully, we'll get somewhere with this, right? So then now we have the union find, and then now we have I mean, I know how to mark an edge, right? So basically, if you find of u is not equal to you find of we, then we need this edge as part of the union, as part of the minimum spanning tree, right? How do I want to mark that though? Yeah, let's just say good edges. I don't know. We'll figure out later, right? And then union UV, right? That's pretty straightforward. And now our good edges will contain the minimum spanning tree, right? And now we want to pre-process it. This is very annoying. We want to pre-process this for LCA, right? I forget how do I? So now we have a tree that is good edges. How do I pre-process it for LCA again? All right. Well, let's create an edge list or an adjacency list. All right, let's do that. Man, my memory is a little bit bad today. Sorry, friends, if you were expecting something better. In good edges. Now adjacency list of new dot append VW, right? Okay, and then now we have the adjacency list. And actually, I didn't really need the good edges. You can kind of put it, manually, but that's fine. I like to kind of keep things one at a time. Okay, now we have the thing. Do we just do a depth first search through the nodes to create a rooted florist? Yeah, okay. I forget how to do the check. Binary lifting. I forget binary lifting LCA. It's been a while. I mean, the thing is, I do remember all the concepts, so I do it fast, so I do it slowly, but probably slowly to be clear. Okay, right. So then now, yeah, the thing that I most have to look for is that now I have to kind of reuse these parents things, so it's a little bit awkward because I like to also call parents in part of the thing, but what do I call it? Let's just say it's here parents, right? Maybe I forget how I structured this, so we might have to do some modifications. But this is part of the practice, right? Okay, so then now we have a depth of search, or just a traversal. Let's go traverse of the node and the parent, right? Yeah, and this is standard. I mean, because we're given a tree, everything should be fine, right? So then now for v in adjacency list of node, if v is not parent, then yeah, then we traverse v and node as the parent. We want to set LCA parents of node is equal to parent, and we just keep going at it, right? And then now we go for I in range of n, right? Yeah, I think, and we can say yeah, if I not in LCA parents, then we traverse I -1. Okay, and then now we have the tree, right? So they just return false, and then now I just want to print out the tree really quickly of the minimum spanning tree. So this is actually a spanning tree parents. Oops. Do 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 do. Okay, so this is what we print out for the parents. 0 is -1, 3. Oh, whoops. Should be W. We might have to. Okay, I mean, I just want to print this out for now. I think maybe I have to use it a little bit more though. Okay, so 0 is -1 because it's the root. Then you have 3 is 0, 2 is 3. And so 0, 3, 2, 1 is right. We're good. 4 and 5 is good. Okay. I mean, it's a very limited. Well, we only have one example for apparently, and you know that's fine. It's right for this one. So let's think. Right. So then now, now is the dynamic programming portion, right? Of the binary lifting. I'm trying to remember if we're supposed to do it pre-processedly, or you could do it just cached. Trying to think. It's been a while, huh? Okay, but I think you could do it cached anyway, so I don't think I need to do that immediately. But okay, so let's say we have this, right? And we probably have to keep track of the weight here. I don't think it's that bad. As long as we could get the parent, we could get the min of the components. It's not that big of a deal, right? So then now I want to construct, yeah, let's say this is just an array of this, right? So then now we have 0. That's pretty much what I need. Well, and here. And 0 just means 1 distance away. 1 means 2, so it's 2 to the 0 power away, right? So then now we have Hmm. I'm trying to think whether I'm supposed to pre-process. It's been a while. Sorry, friends. I know that you didn't quite quick to watch me, whatever, but deep, I mean, it is what it is. It is definitely something that you know, I want to emphasize that, like I said, I'm doing this live with all from memory, right? So, and it's something that I haven't done in a while, and I'm trying to figure out the best way to do it. I mean, I know how to do it. I just try to think about it in terms of cleanliness and stuff as well. Actually, I don't know why I do, because n is 10 to the fourth. I think I'm overthinking about it because I'm trying to optimize these things in my head. But yeah, but the matter is that 10 to the fourth is what, 10,000. 10,000 is less than 2 to the 16, right? 2 to the 16 is 5. So 2 to the 12. What is the 14? Whatever, 2 to the 14, right? So then we're definitely good. So then now let's just say rep m is equal to how do you get the let's say binary of the length of the binary bits minus 2 will be the number of digits, right? Yeah, roughly. Maybe I'm wrong on this one. But then now we can do the dynamic programming, right? Of LCA. Then now LCA parents of, oh, start from 1, whoops. From I of I, oh, not I of I. We need another thing. That's why I'm confused. In range of n, right? So I of j is equal to LCA parents of I minus 1 of j. So then this is one level parent, and then is this parent, right? So it's parents, something like this. And that's pretty much it, I think, right? I spent so long thinking about this, and it's really not that bad. I don't know. Let's print it out real quick for maths. Ooh, -1. I cannot be -1. Can J be -1? Oh, because this is -1. And this is -1 because it is a root. Okay, that makes sense. So then now, if is equal to -1, I don't. The thing with not practicing is that there are all these like random edge cases. Is why. Did I miss that? Why would this be out of bounds? Oh, of course it's out of bounds, because why did I do it this way? Why did I? What? Huh? I don't know. Okay. Let's just say it is none times. Why did I do it this way? Huh? Why did I use it? I think I just wanted to make sure that I was in the right place, but I guess that's fine. Inner is n. Okay, so we have something. It may not be the best, but it's fine. Yeah. So the one I'm gonna say is zero's parent is 3. Is that right? That doesn't seem right. Did I mix the order up in the traversal? The parent of node is parent. No, that seems right. So it is this graph. So on 0, zero's parent is 3. Is this deterministic? It wasn't the same as before. Oh, maybe I read it in the opposite direction. That doesn't make sense though, because we always traverse 0 first. So, wait. I guess the 0 node is just this one. I think I just messed this up. I think. No. I parent we know no. What am I doing? I mean, I think I for some reason this is the opposite way, which is fine. But I want to make sure that it is what I thought it is, because it's not. I don't want to keep going and then like have to debug this later on, right? Like you have to debug it here or now, and here it is more clear than before, in theory. Oh, because the not in is no longer true. So okay, so if is none. Oh, I'm just being dumb. Okay, there you go. So it was doing crazy. Okay, there we go. Okay, see, I converted this into an array and I forgot to change this part. Okay, fine. So then now zero's root is 1, 2. One's parent is 2, which is good. 2's parent is 3, which is true. 3's parent is 0, right? And then now 2's two-step parent is 0. One two-step parent is 3, so that's good. And then there's no 4-step parents. Is -1 the best way to do it, or is it the root? I don't know. I don't know what's the convention. I feel like it should be whatever, but okay, fine. I mean, it should be fine either way, just different base case handling. Anyway, now we have the LCA, which is good. Now we have the thing, right? And actually now what we should do, what I should have done, and we can still do, is that we want to add LCA weight, right? So then now this gives us the weight from here to the parents, and this is now a sparse table really, but it's a very kind of, I don't know, sparse table with respect to it's not quite the same as the sparse table because the stuff is represented a little bit differently, but it is kind of like a sparse table, right? So yeah, so then now we have this, and here we want to say, okay, I mean this is nothing, and then here we want to say LCA weight of from read to node, or oh wait, this is just 0 from read. It's going to be equal to weight. Okay. Okay. Let me just print it out real quick. And that's the thing with practice, right? Is that you don't have to keep printing things out if you're used to it. But yeah, 1 connects to 2 with the weight of 3, so this looks right. Everything looks good, right? And then now we can do something like, I mean, this is just gonna be none anyway. So now we can do something like min of LC weight of I minus 1j, or this thing, right? Because basically now you're merging the edges. So yeah, so how I'm able to kind of prove all this is because or I don't know if you consider it a proof, but the reason why I'm able to come up with all this is because I have a very solid visualization of an understanding of the algorithm. I might not remember the implementation, and clearly I don't. But once you have that, then, you know, if you really understand it, it could be a long time and you can still remember it. And it's been a long time for me, to be frank. And probably the last time I did this, you've seen it on video, or you can see on video if you watch a video. But you know, I don't remember when that is, to be honest. But yeah. All right. Then now we're good. We're good with the setup, I think. Let me print out this again. Just why not? Wait, ooh. Oh, because some of these can be none. I guess we'll just do it as infinity, right? That's fine. Okay, so then now we have infinities, which is fine, I think. Oh, it's not the min, it's the max, right? Because we want the max. Okay, yeah. Oh, well, then now this is no longer it's negative infinity. Okay, good. Okay. Yeah. I mean, this roughly feels good. It'll be a little bit awkward. What is this? This is one, but then it goes 4. So why is this 3? Oh, because the other is negative infinity because it goes too far. Maybe that's fine. I don't know. We might have to play around with some edge cases. But yeah, I mean, I did anticipate this one to be a long one, which is why I was like kind of not stressing, but I was just like cancel all my plans kind of thing, you know. At least for me. Okay. So, okay. Now we have to find P's and Q's. So then now we have to figure out. Oh. Maybe. Oops. I have to put it into the self. Right. And then now we have to basically just do a P and Q lookup, right, of LCA lookup. How do I do that is with binary search, right? How do I write the binary search again? I mean, I know. I have an idea. I mean, I know the concepts, but I always forget because there's a cleaner way to write it, and I always don't remember how. Which is that you take the biggest bit and then you see if you add it. Because I think the Chinese are very fond of using it that way, but I've always been really bad at that particular way. Because I'm just used to the bisection method of binary search and not the take the biggest bit and then see if you want to add it kind of way. But we'll try that. Yeah, right. I would say maybe self.m is equal to m, maybe self.n. I don't know if I need n, so I don't know. But yeah, okay. So then now we say, get the LCA, right? Okay, right. So then now for how do people? I mean, this is a good time to learn anyway for me. So we have m, right? So then now we have binary search. So current is equal to 0, right? And we have for I in range of m minus 1. Is it m or m minus 1? No, it's m minus 1, I think, because, and then it's 2 to the power of I, right? So then now we want to see where this thing is. So okay, so then now if with self.lca parents of something and p, right? So then now this is going to be I. Is that right? No. I mean, it is kind of right, but how do I do? So then, okay. Do we add this part? So this is just me checking whether we add this part as p. And if we do add it, what does that mean? Then you shift the parent, right? Maybe. This part I'm definitely a little bit weaker at. Let's just say ancestors equal to none, maybe. Yeah, okay, whatever, right? I don't know. So if this is not equal to, or if this is equal to -1, we've gone too far, then yeah, then we don't add, right? Then we continue, I think. Otherwise, if parent is how do I check if something is a parent of something again? It's an is ancestor function, but I don't. Why am I so bad at this? This part I actually don't remember as well. How do I check that this node is the ancestor of Q? I guess that's what I want to do. So this means that this is out the tree, right? So then now we have to check like is ancestor of Q, right? But I don't. How do I write that? I don't do another binary search. Man, come on, Larry, you could do this. You've done this entire way. You can figure out the rest, maybe, hopefully. But yeah, in this case, then now, if this is the case, that means that you've gone too far. So you actually don't add, right? Because otherwise, then now you add it. And the reason is because then you move it forward. And actually, you don't even need, I don't need to how far away it is. So actually, I would just write ancestor is equal to this thing, because then now we move forward a little bit. We moved it forward at least halfway, because the assumption is that the previous loop is an ancestor. No. But then now that how did I write this? Huh. I forget how to do it, to be frank. I thought this would be the easy part, but I just forgot. It's been a while. Huh. I know that there's like a very cheap O(1) way of doing it, but maybe I'm wrong. Why did I forget this part? I and P. So you have a node. I mean, I don't want to do another binary search on that. I don't even know if that works. Am I missing something? Oh, I do remember now. Oh, right. I think one thing that I had to do is do a depth of each node. Okay, fine. Whatever. I mean, I think it's just a node, right? So then now we can, where's my recursion? Okay. And then now we can do it, because basically Okay, I mean, now there are a couple of ways I can write this actually, right? Let me think about the cleanest way to write it. I have to. Because they're now in the same depth. Okay, yes. Man, I do not. Because the reason why I don't remember this part is because usually when I do binary lifting, I proved it from scratch. I've never actually learned binary lifting from something. But also, to be honest, because I learned binary lifting kind of in that I actually learned sparse table first. And in that, you don't need the depth because you convert it to a 0, or you can convert it to a +1 -1 thing. So in that part of the LCA, you actually convert it to RMQ, and then you want the sparse table. I guess. I mean, yeah, because yeah, okay. I mean, sorry, life story. But yeah, because there are two ways to kind of think about binary lifting, or there are two ways to do LCA, I guess, if you want to be more specific. There's the way of what I'm doing now with binary lifting, which I've only done once or twice, maybe 3 times in my life. But because the way that I was taught when I was in, I guess, grad school, if you want to call it that, or grad level algorithm class, is that you would convert it to an RMQ, and then the RMQ will get you the answer. And I've always coded the other way with RMQ, so this is new for me too. Okay. So then now, okay, how do I want to write it? Okay, I mean, yeah, that P is equal to self dot depth of P, right? And depth Q is equal to self dot LCA depth Q, right? And then now, yeah, I don't know, delta depth is equal. I don't know how to write this. Okay, with depth P is greater than depth Q, then we want to move P is equal to, let's just say move P delta up, and then this pseudocode obviously move Q delta up. Okay, right? We'll do the binary search later. Maybe not delete it, but yeah. Okay, so then now we want to say, all right, we'll have a move P delta depth, or depth P minus depth Q, and then move Q depth Q minus depth P, right? Yeah. And I'm just want to save this just in case I need it. So old P, old Q. Right. Okay. Okay. Yeah. And then now, and here we write P is you're gonna move it up. All right. And then now we write the move function of node delta, right? Okay. And then here, yeah, we can do it in the same loop, right? For I in range of m -1 -1 -1, right? And then if 2 to the I is less than or equal to delta, then delta -1 to the I, and then node is equal to self.lca parents sub I of node, right? And then now we can return node. Okay. Whew, okay, I think that's relatively correct. The annoying thing is that what I would like to do right now is just to test this real quick. And we will do that. What's that, true or false? Okay, fine, just return. But yeah, so then now we can print P depth P, but the example input that they have is not very detailed, so we have to be a little bit careful. And then after move is going to be PQ. But let's run it real quick anyway, and then maybe we'll construct something if we need to. Okay. List assignment. Oh, whoops. Right. So now we have 2, which is step 2. That's true. 3, which is step 1, which is true. And then now we move this 1 upwards. Okay. I mean, these are not interesting enough cases. That's why I'm like, you know, 1 is step 3, and then we move up twice. It goes to 3. I mean, that looks good though, but it's just that, yeah, it's not very interesting. They're on the same depth level. Okay. I mean, yeah. Yeah. I mean, it's fine. It's just that I wish there were one more, like, more tricky examples that I can manually move this before going on. Because the thing is that if there's a bug in here, then we want to debug this knowing that there's a bug here and kind of sanity check it before we move on to the next part. Now we do the binary search, so it should be okay, which is that, okay. So then now if, okay, so now they're in the same depth, right? So depth is equal to depth of P, right? So, I mean, P or Q, it doesn't really matter because they're the same, or they should be. And then now we go, okay, right? So if, how do I write this? Yeah, if this is greater than depth, then we have to go too much, so then we just continue. And you could probably just do a math so that it doesn't start off that way, but I'm lazy, right? So then now this should not be a case unless we messed up. But then here, now, if move of, this is exact, so it's a little bit awkward. Okay, fine, right? So maybe we need to use this, but if self.lca of parents of I of P is equal to self.lca parents I of Q, what does that mean? That means that they have the same ancestor, which means that what does that mean? I mean, that means that we can try something smaller for sure. Okay, so let's say they're different. What if they're different? If they're different, that means that we have to go higher, right? Man, this binary search I always struggle with, so maybe this is a good time to learn. But okay, so that means that we have to go higher. That means that we definitely want to move this up. If they are equal to, but that means it's a little bit awkward, but okay, fine. Right? If they're equal to, then we don't do anything because we're going to try to get something smaller, but it is, so then it'll be the parent of the answer. Okay, I think this is right. So that means that if they're not equal to, then we want to say P is equal to move, you know, we move this exactly, which I guess I don't need to write it like this, I think, because this is exact, so I can actually just write self.lca.parents of I of P, and then Q, we move it up. And then in theory, no, I mean, it is true. But we have to consider the weight at some point, but that's fine. I'm okay with not considering the points yet. Okay, and then now we go to P and Q. Yeah, let's do the old P and Q. And then here is the new P and Q. There should be one step back unless they already are the same. Okay, I don't know what I wrote, so okay, after. So before, after, okay, after is that's weird because they're not the same. Why? Oh, because the before is before we move this thing up. Okay. That's why I needed a more complicated thing, because I think after you do the same depth thing, that's why they don't change afterwards. So it doesn't mean anything here. So I need one more case. How do I want to write it? I need another edge of let's just say 7, right? So 2, 7, 1. It doesn't matter, right? The idea here is going to 2, 6, 1. Whoops. The idea is that if we query for 1 and 6, it should give us something a little bit interesting. Okay, I mean, if I type it correctly anyway. Oh, I have to do another thing here real quick. Okay, so then now 1 and 6, after they're on the same depth, and then after they're 1 and 6. Okay, because then now we know that they should be 1 away, right? and then now we just accumulate the max along the entire route, and basically the LCA should be the parent of P and Q, I think. If they're not already the same from here, I suppose. Same depth. If P is equal to Q, then we're done. We return something, but we have to return something, but we have to do the weight part. So now I think we did the LCA part, right? Now we have to kind of do the weight part, which is here. Okay, so then now maybe weight is going to be equal to -infinity, maybe, I don't know. But here on the move part, we will say here non-local weight is equal to max of weight, and then because every time we move, I guess we only do it here, we count the weight that is upwards. That's going to be self.lca max weight. Oh, not LCA, what am I writing? LCA weight of I and node, but you have to do it before we move. Okay, right? So that's on the move. Assuming they're not on the same depth. Return weight is less than or equal to limit, or strictly less than limit, right? All right. And then otherwise, every time we move, we go, okay, weight is equal to max weight self.lca weight I of P. And again, we have to do this before we move, and we do it on the other one too. Yeah, and then now right? Just one step. Assert that P is not equal to Q, because if P is equal to Q, we will have returned, and I think this binary search allows us to get to this. Here, then now we also do this on the weight. And then now they I'm trying to think what happens if they're disconnected. That's what I'm trying to work out. because they're in the same depth, and now it goes, they're not going to be the same. So then it keeps going up, and then now we're at the root. But yeah, okay. So then now, if P is -1, I think I wrote. Is it? No, it's none. No, it's -1, I think, yeah. If P is equal to -1, then we return false because it's just not connected. Otherwise, we return rate is less than or just less than limit. Let's give it a spin. I know I have some print statements, but it looks okay for the examples. Am I confident? To be honest, not really. There's a lot of silly things I could have done here, but good enough for me to submit. And YOLO and alright. Yay, we Gucci. This took an hour. I'm just checking real quick. Union Find and snapshot. I guess snapshot was how I kind of thought about it as well. But I definitely did this thing. What it? Yeah, okay, fine. I mean, I'm not a fan of. I was thinking about that, but I'm not a fan of that. But yeah, I did the minimum spanning tree binary lifting one. But I mean, at the end of the day, it's just about what you want to practice, and I did practice binary lifting. That was pretty good. We worked everything from first principle. Like, I don't think this is the cleanest or most concise or precise or whatever code, but everything's from first principle, right? So I'm pretty happy about that. At the end of the day, you know, memory is not memory. It's about what you can do with problem solving and remembering these concepts. And remembering the concept is more important than remembering code. And I'm pretty happy that I got it right. I mean, also, just to be clear, I'm actually surprised that I got it right. I mean, not that, like, I knew that the algorithm was right because, I don't know, just experience. And it's greedy. We talked about like greedy, and I mean, these are just things that make sense. I don't think this, like, maybe I don't have a strict proof, but it makes sense that it was right, and I was very confident about it. My not confident is about the implementation, and definitely there are a lot of ways to mess up the implementation. And I expected to mess up the implementation, to be honest. So to get it right on the first try was actually quite surprising in a good way, because I've definitely made a lot of silly mistakes on sillier problems. And like I said, I think maybe this is the third time ever I've done binary lifting, and from scratch, because I forgot about the depth part. I was like, and there are a couple of ways you could have written this part as well. I have to step through the binary search. Yeah, I mean, the way that I did this is a little bit funky, but you can. I mean, it is actually optimal, and I have to kind of think about all this case. But you could also, like, if you were lazier or just a little bit unclear, you could actually do a binary search on the move function, right? Because then now you just delta on some number and then go through it. Of course, you have to kind of skip the rate for it, but then it becomes like log square n instead of log n or something like this, right? Which is not that bad, to be honest. But you know, I'm here to learn, and this was a good chance to play around and learn. Yeah. What's the complexity here? I don't think I went over it, even though everything is pretty low in complexity. This is why I didn't really question it that much. It may be that, you know, this is E log E. Union find is effectively linear time, linear space. I know at reverse argument, and I know I didn't do order by rank stuff, but yeah, whatever, right? Like, hand wavy a little bit, right? We have, union find and minimum spanning tree. This is linear after the sorting, right? So this is, yeah, because we look at each edge once, right? So it's still dominated by E log E. Adjacency list is linear. What do I have here? This is just a depth first search, right? So a traversal, a tree traversal. So this is going to be linear. And here, this is O of n log n, right? Or where n is the number of nodes, not the number of edges. And this is, yeah, this is sparse table, right? Pretty much. I forgot the depth part. It is what it is. Took me a while to remember it. But yeah, and then so that's this part. So what did I do? So everything on the pre-processing side is going to be relog v plus elog e, right? Because this is relog v, and everything else is elog e, or specifically the sorted list. And you could write in a number of ways, but whatever. And on a query, so that's the pre-processing. On a query, everything, this is O of 1, this is O of log n, which is O of m, as I have it. Do a couple of these, or just, yeah. And this is a binary search, which is log m, right? This is why, we move it. Oh, actually, I don't even move it. I just kind of, well, I do move it, but it's an O of 1 move. And yeah, I don't know if I explained it that well, but the idea here is that every time you move up the tree, you want to get the maximum rate on that edge, and that edge is constructed to you as part of the LCA, right? And basically just kind of combine, and the beauty about this is just that you're maxing all these at most m components, which is log n components, and yeah, and they get smaller over time. But yeah, that's all I have for this one. Let me know what you think. This is not an easy problem. It took me an hour and I knew exactly what I wanted to do. That said, maybe not exactly. Like, I knew algorithmically what I wanted to do. I spent like 15 minutes trying to think about another way. And I don't think the snapshot way is easier, to be frank. Maybe I'm wrong. I don't know. Right? And so, yeah. But everything's from first principle. If you really want to learn binary lifting, I don't know that this is a good video for learning, but it is a good video to see someone implement it and try to figure out every component from scratch, right? So yeah, that's all I have for this one. Let me show you the code once more. This is the pre-processing, union find, minimum spanning tree, DFS kickoff, sparse table, or just dynamic programming if you want to call it that. And I didn't go over it that much here with respect to proof for dynamic programming, but it's just that basically, if you think about it in terms of like, I think about it like train stops, kind of, in that, okay, how do I, like, if I'm on a train and I know what my next stop is, right? Well, what's 2 stops away? That's just next stop. Right, so then now you have this next stop, and then so what's 4 stops away? Well, that's just taking 2 stops and then taking 2 stops, so that you combine them to store the 4 stop away, and then you do that for 8, and then so forth, and of course that's going to be log, that's repeated doubling, and of course there's going to be log n times, and yeah, and you could use that to build out other things, and because in this particular problem we're using max of overlapping things is actually way cheap. Right, so that's fine. And in fact, I didn't do it. You could have done it this way, where if you know the distance, you can actually do this and even faster. But not gonna go over that. But yeah, that's all I have for this one. Let me look over the query real quick. So this is the query. This is just the moving up, right? So you have a given delta. This is just whatchamacallit. Like, yeah, basically you have a binary number with the components, and you sum up the components to get that binary number, kind of, to move. Like, for example, if you have to move 10 steps, that means you have to move 8 steps, and then you have to move 2 steps or something like that, right? That's the idea. And of course, this is just so that we get to the same depth, so that the next part is easier to write. There may be other ways to write this, but that was generally my idea. Here is just binary search, right? It's just to see that, like, if taking a train 8 step, we don't meet at the same if we do meet at the same time, that means that we probably gone too far, so then we want to go one below that, right? That means that we'll try again in the future, and if it's too short, then you eat up that distance and then keep going. And because this means that it'll give you the 1 stop before that, which is why I have this thing to move it to the parent. And I even have an assert to make sure. And this is if you're already at the root, then it's going to be false because and this is the root. And I figured this out from scratch, by the way. I didn't memorize these edge cases, but I figured out that if this is always false, then we're going to keep on going to the parent and all the way to the case where and because it cannot go on the depth, that means that the depth is going to be 0 at the top, and with p is not equal to q, after getting the parent, then it's going to be that means that it's at the root, and if these are roots, then the parent is going to be -1, which is why I have this. Otherwise, then we just return the way. That's what I have for this one. Let me know what you think. Pretty tricky problem. Took me an hour. Stay good, stay healthy, do good mental health. I'll see y'all later and take care. Bye bye.